Previously, we did an example designing a column which is subjected to moment in both axes. Now we're going to do another example dealing with the same column, having the same set of details and specifications, except that the column is braced and slender. The purpose is to demonstrate the differences in terms of the calculation steps due to the changes in terms of the conditions of the column. Without further ado, let us get started. Our first step is to determine the nominal cover. The calculations is typical. First determine the C mean and then determine the C nominal. The nominal cover is calculated as 35 mm. Next, we need to determine the MED. The calculations of the MED it will be depending on the column's conditions. In this case, we are dealing with slender column, brace structure. Slender column, brace structure. You may sketch the stress diagram here and then work out the equations to determine the MED of the column. You see, you need the first order moment as well as the second order moment in order for you to work out the MED. The calculations for the second order moment it will be unique to slender column. If you observe the calculation steps of the previous example, the calculations of the MED does not involve any second order moment. Therefore, it will be starting with the first order moment. First, determine the moment due to the imperfections, which is calculated on the basis of the absolute multiply the eccentricity EI. Eccentricity EI is determined by the effective length divided by 400. The effective length for the major and the minor axis are given here. Having the effective length divided by 400, you get EI equals to 12 mm and also 10.9 mm. Multiply with the absolute, which is 147.36 kN. You will have your M imperfections 1.8 and 1.6 for the major and minor axis respectively. You will need to calculate both major and the minor axis since you have moment acting on both axes. Next, you need to determine the M02 and M01. If you look at the equations for the MED, you need M02, you need M01, and you also need MOE. Therefore, all these three needs to be calculated. Let us first deal with M02 and M01. For the moment given in the questions that acts on the columns in the major and in the minor axis, the given moment will need to be plus with the moment due to the imperfections. The bigger value of the two shall be the M02, whereas the smaller one will be the M01. Same goes to the minor axis. Let's say we need to calculate the M02 for the major axis. The moment acting on the major axis is 26.6 and 15. The bigger value it will be 26.6 plus M due to the imperfection, which is 1.8. You get 28.4. As for the smaller major axis moment, which is 15, plus M due to the imperfections, you'll get M01 16.8. You will do the same for the minor axis using 13.3 and 7.5 kN meter plus the M due to imperfections 1.6 kN meter. With that, you have obtained M01 and M02. Next, you need to calculate the MOE. Based on the equations, it is calculated on the basis of 60% of M02 plus 40% of M01. That means we are talking about this times 0.6 plus this times 0.4. That gives you 23.8 kilonewton meter. You will do the same for the minor axis. This times 0.6 plus this times 0.4. That gives you 12.6 kilonewton meter. The calculated value should be at least greater than 0.4 M02. That means this number is calculated by multiplying 28.4 with 0.4. Same goes to this. 14.9 times 0.4, you get 6. The bigger value of the two shall be the M0E. Since these are bigger than this, therefore the MOE you get 23.8 kilonewton meter in the major axis and 12.6 in the minor axis. Next, we want to determine the minimum moment, which is the M-mean. As determined in the equations for the MED, M-mean will set the minimum moment that you use to design a column. The M-mean here is determined by the Asian loops times E-note. E-note is calculated based on H per 30, and it should be at least 20. The H here, you have to be careful with the axis. If you are dealing with the major axis, your H it will be 300, which is the larger dimensions of the column. If you are dealing with the minor axis, your H now it will be 150. 300 divided by 30, you get 10 mm, and 150 divided by 30, you get 5 mm. These two values are less than 20 mm. Therefore, you will use the E-notes equals to 20 mm. Multiply with NED 147.36. You get 2.95 kilonewton meter as the M-mean. Next, you need to determine the second order moment, which is M2. M2 is calculated based on NED times E2. There is a series of equations to calculate E2. Most of the equations you have those values known, except for KR here. KR is a correction factors, which at the early stage of the design, you have no idea about the amount of reinforcement bar to be provided in the column. At the moment, you do not know the AS. Not knowing the AS, you cannot get the omega. Not able to get the omega, you can't get the NU, and therefore you can't get the KR, and subsequently you can't get the M2, which is the second order moment. In order to solve this problem, we have to start from somewhere. Therefore, normally we will start with assuming the KR equals to 1.0. Later, once we have obtained the M2, and subsequently we obtain MED, and then we're going to check whether the biaxial bendings are giving effect to the column. If yes, we will have to incorporate the effects due to the biaxial bending. Only then we'll use the design chart and get the AS. Once you have obtained the AS, you will substitute the AS into the equations and check your KR against what you have assumed previously. If the KR assumed is the same as the calculated, that means the M2 it will be the one as per initially assumed, and the MED shall not change. Now in the case that the KR calculated is not the same as what was assumed, that means there will be corrections to the M2, which subsequently will be corrections to the MED, and then from the design chart, you will obtain a new AS. Bring the new AS back again and test the KR again. This is until you get more or less a constant KR, which leads to the same M2 and the same MED. Only then the amount non-reinforcement bar is confirmed. It may seem to be quite complicated. After this example, we will spend some time to explain the design process. Coming back to this example, now your intention is to determine the second order moment. Same thing, you're going to calculate for the major and the minor axis. Go through a series of the equation here with the assumption KR equals to 1 for you to work out the E2. Let us first deal with 1 per R0. It is given in the equations epsilon yd divided by 0.45d. The design yield strength, it will be calculating from the design yield stress divided by modulus of elasticity of the steel. FYD is determined as 0.87 FYK, considering the partial factor of safety for the steel material. Therefore, FYK given in the questions 500, multiply 0.87, you get FYD, design yield strength of 435 Newton per mm square. The modulus or elasticity of the steel is 200 gigapascal. This is given in the Eurocode. Substitute the value into the equations, you get your design yield strength equals to 0.00218. Next, you need the D. Calculating the D, you can sketch the reinforcement bar in the typical column. We are talking about the effective depth in the major axis as well as in the minor axis. The effective depth is calculated by the H minus the concrete cover 35 minus the shelling 6 mm and minus half of the bar size, which is 20 mm divided by 2, as expressed in the equation here. For the major axis, your H it would be 300, whereas for the minor axis, your H it would be 150. Since the dimensions of the column is in the rectangular shape, this gives you 2 ratio of 1 per R0. Next, we need to calculate the creep factor. The creep factor is calculated on the basis of the beta and also the effective creep ratio. These are the relevant equations. Let us first deal with the effective creep ratio. These two are with the values assumed. Multiplying this 2.3 with 0.67, you get the 1.541. And then you need beta, which is in the functions of SCK. The FCK is 30, and also the slenderness ratio. The slenderness ratio for the major and the minor axis are given here. Depending on the axis that you are looking at, you will have 2 different beta. Substitute the beta into the equations and also substitute the coefficients of the creep. You get the creep factor for the major axis 1.2 and for the minor axis 1.0. You will need to make sure this creep factor here needs to be at least 1.0. How do you get this value? 1 plus 0.13 times 1.141, you get 1.2. You will do the same here. As for the KR, at the moment we don't know the amount of reinforcement. We will simply assume KR equals to 1.0. Now that we have 1 per R naught, we have the creep factor and we have the correction factor. Our next step, it will be to calculate the curvature 1 per R. Referring to the equation here, you have 2 ratio of 1 per R naught. You also have 2 ratio of the creep factor, and then both you will use KR assume, which is 1.0. This will give you 2 curvatures. And then the following step is for you to determine the E2. You need the curvature, you need the C factor. C factors is equals to 10 as given in the Eurocode. And then you need the effective length, and this effective length needs to be squared. The effective length for the major and the minor axis are given in the question. Use the right effective length for you to work out the E2 for the major and the minor axis. Having the E2 calculated, multiply the MED 147.36 kN. You get M2 equals to 7.8 and 13.4. Now that you have all the first order and second order moment plus the N minimum, substitute into the equation. Get the M02, which if you are referring to the major axis, M02 equals to 28.4. You need M0E plus M2. M0E for the major axis, 23.8, plus M2. M2 is equals to 7.8. The third item, M01 plus half of the M2. M01 is 16.8 plus M2, 7.8 divided by 2. And then lastly, your M min, which is equals to 2.95. Among the 4 items here, you get the largest value, which give you 31.6 kN meter. You will do the same for the minor axis. M02 equals to 14.9. And then you need MOE plus M2. MOE is 12.6 plus 13.4. And then you need M01 plus 0.5 M2. M01 is equals to 9.1 plus half of the M2. And then lastly, you need M min, 2.95. Among the 4 items, you choose the greatest value. That gives you 26 kN meter. Now that we have estimated MED in the major and in the minor axis, since the column is subjected to moment in both axes, designing for the reinforcement bar based on the major and the minor axis separately might underestimate the design load. Therefore, this number shall not be used directly. We will need to check if biaxial bending check is required. If it is not required, then you may use these 2 values for the design. Work out the AS for the major and work out the AS for the minor, and then come up with a same common layout of reinforcement. Now if the biaxial bending check outcome shows that you cannot ignore the effect of the biaxial bending, then either of the major or the minor MED will have to be revised. The new MED shall be used to design for the reinforcement. We're going to discuss about this in our following videos.